профессора Джереми Вольфа, профессора Гарварда, одного из самых влиятельных психологов в изучении внимания и восприятия, в частности, задачи зрительного поиска, и автора модели направленного поиска. Мы очень благодарны Джереми, что он приехал, согласился поучаствовать в нашем семинаре «Великой иллюзии». И сейчас представляем лекции. Еще продолжение его лекции будет в Москве в понедельник. Поэтому, если вдруг вы захотите еще раз послушать, вы можете переместиться в Москву. И тем не менее, мы сегодня завершаем нашу работу семинара лекции профессора Вольфа. Завтра семинар начинает работу в 10:30, аудитория 118 для тех, кто забыл. Спасибо. So, we're really happy to hear, and we really appreciate that you have come here, and so.
Thank you. I have no idea what you just said, but you're still here, so it's probably okay. Can you hear me in the back? Yes. Good. Can you hear her in the back? And you should sit someplace where you can see the pictures.
Пожалуйста, садитесь, чтобы было хорошо видно слайды.
So I've never been to St. Petersburg before, and it's beautiful.
Раньше никогда не бывал в Петербурге, это замечательно.
And I changed the talk because it's St. Petersburg. No.
Я решил поменять тему выступления, потому что это Санкт-Петербург.
But because this talk has more to do with the mysteries of consciousness.
На самом деле, потому что эта тема лекции имеет большую связь с проблемой сознания и загадкой сознания.
So we should have a rule that if somebody wants you to, if they want you to translate, they should like wave their finger or something.
Да, давайте, скажите, пожалуйста, перевод нужен вообще или нет?
Нет.
Может, наоборот, вопрос поставить? Кому нужно?
Нет, I understand, but I don't know what the question is. Oh, that's the question. Now she's leaving.
Если перевод кому-то нужен, приходите, пожалуйста, к нам сюда.
Okay, well, whatever. Okay, so.
Okay, I'll do it here.
Oh, you're doing it there?
Yeah.
Okay.
I'll translate here for those who need it, and just invite people who need it. You just talk.
So, here's what I will talk about today, I hope. We do visual search tasks all of the time, continuously. We also pay people a lot of money to do some very important search tasks that they do not do perfectly. And we want them to do them perfectly. So, I sit in a radiology department at Harvard Medical School. So I have a lot of interests in things like this. This is an image of the breast for looking for breast cancer. So there's a very hard visual search task. This is a picture from when the Malaysian jet disappeared into the Indian Ocean. And they sent very fancy equipment to go and look for where this plane had gone. There was an article in one of the US newspapers where they interviewed the pilot of this plane and said, what is the most important piece of equipment that you have on this plane? And he said, it's Joe, he looks out the window. So we're interested in visual search generally. We, of course, study it under laboratory conditions. And what I want to argue is that these laboratory search tasks can tell us something about how we do expert, socially important, difficult search tasks. And I will also tell you that what we learn from experts tells us about visual search in general, including the sorts of experiments that we do in the lab. So I should always, this is a small number of people whose pictures I should show, but 3 of my postdocs, 2 doctors at my hospital, their work will show up in this talk. And I will have 3 parts, I think. I will tell you that visual search is guided. I will tell you that visual attention is very limited. That will be the part that is most relevant to this question of consciousness. And I will tell you something about how we make decisions, particularly decisions about when to stop searching. When is it time to decide that a search task is over? All right. Why do we have to do search at all? Do you remember the first slide, my title slide? You had all these red and green pluses on it? Which one did you see? Yeah, right. Who knows? Okay, that's not fair. That's memory. Let's do it this way. Look for the plus that is red vertical and green horizontal. Okay, you ready? Look there. Yeah. Okay. Did you find both of them? Yes. Good. Okay, that's a good group. So what is important here is that as the moment that the stimulus appeared on the screen, you knew red and green pluses everywhere, right? But only when you attend from item to item can you tell which plus is which. You need to pay attention in order to actually identify the object. This is called binding in the, well, at least in the English literature. Okay, Masha, what's binding in Russian for these purposes? Okay. So, the point is that before you pay attention, this is red and green and vertical and horizontal. And this is red and green and vertical and horizontal. Only with attention can you decide how the features go together. This observation about binding is most associated with Anne Treisman, not with Barack Obama. But Barack Obama gave Anne Treisman that prize. It's the highest science prize in the US. So, you know, keep working on experimental psychology, you win the big prize. Okay, so to recognize an object, you need to bind the features. To bind features, you have to attend to an object. And so if you have to find the specific object, then you have to search through the scene. That's basically, we think, why you have to search. Now, why does this have anything to do with radiology, or why is it interesting to radiologists in my medical school? Because there is lots of evidence that many errors in clinical radiology and other domains are due to really errors in visual attention, errors in visual search. Here is a hint that that might be true. You get articles that talk about retrospectively visible, unreported breast cancer. What does that mean? What it means is, so if you're being screened for breast cancer, in the US, if you're between, after 40 or 50, a woman would be screened every year. If you find something, if the doctor finds something in 2014, the first thing she does is to look at the films, the images from 2013, because she wants to know, did this grow? But what you find at very high rates is that when you look back at the 2013 image, the cancer is there already. It could have been seen, but it was missed when it was looked at the previous year. And those are not because the image is hard to see, it's not because the doctor is a bad doctor, it's because the search didn't work right. And if we could understand that, we might be able to find more cancers earlier, for example. So, what do we know about visual search from the lab that might help in tasks like looking for breast cancer or lung cancer or other tasks like this? So, first thing I will tell you is that visual search is guided. One way to see that is to look at, these are old data, not data, this is data from before when most of you were born. This is data from Kundel's lab. They measured eye movements. What you're looking at here, here's the lungs. This is an outline of the lungs, and the lines are eye movements. And here you have beginning radiologists, and here you have expert radiologists. What you can see is that what changes as they become more expert is that the radiologists make fewer and fewer eye movements because they now know where to look. Their attention is being guided in ways that a novice's attention is not being guided. Now, we can study this in the lab. It's hard to study radiologists. In the US, they are very expensive subjects, and they don't have a lot of time. So, I want you to look for a 5. I will put up some 5s and some 2s. Look for the 5. Oh, you can clap when you find the 5. Right? It's okay. That's pretty easy. Right? Why is that easy? Because the unique colored item immediately attracts your attention. Your attention is guided to novel items, and that happens to be the 5, and so you're good. Okay, try it again. Look, clap when you find the 5. You could hear it took significantly long. It's not hard, right? Well, it would have been easier if it wasn't a Russian 5. Anyway, so it's easy to tell a 2 from a 5, but you had to search this time. Here's one more. Find the green 5 this time. So again, you need to search a little bit, but you didn't waste any time looking at red items. Your attention was guided to the green items. Here's the way we collect data on this in a typical experiment. We vary the number of items on the screen. That's known as the set size. Is there a good Russian word for the jargon for set size?
Размер набора стимулов.
Okay. Is that just number of stimuli?
Количество объектов.
Yeah, okay. Anyway, whatever it was. And we measure reaction time, the amount of time it takes you to say, yes, it's there, or no, it is not there. This is in milliseconds, so that's 3 seconds up here. If you are looking for the red thing among green things, or the green thing among red things, that first example, it does not matter how many items are on the screen. It just pops out, and you're immediately guided to the target. If there's no guiding information except that you can tell where the items are, the reaction time increases roughly linearly with the number of items. You can, from these sort of data, you can estimate the rate at which items are processed. And that depends on your model a little bit, but about 20 to 40 objects, items per second. Very quick, but still you still have to attend from item to item. This is much faster than eye movements, right? Eye movements, if you need to use eye movements to find the target. So if they were small or they're words or something, you can only do 3 or 4 per second. But if they're big enough that acuity is not a limit, you can do 20 to 40 per second. And if you have partial information, like the green 5, the data lie in between. And you want to know more about this, you ask Igor, who knows everything about this. So I was showing you guidance by color. There is a limited vocabulary of basic features that will guide attention. We fight about exactly what the list is, but there are some that everybody agrees on. You can find the item tilted left among items tilted to the right. You can find the curved, you can guide attention to the curved items, to the little item. Some more complicated attributes like the lighting direction. This cube is lit from the bottom. It's easy to find among cubes lit from the top. And then there are a lot of things that just do not work, even though you might think they would. So, here, until you search, you won't know what the target might be. It's the X junction, the plus, among T junctions. If you happen to be a vision researcher, you know that line junctions are very important. These T junctions like this are signs for occlusion, X is not, but you have to search for it. You cannot guide your attention to a particular kind of intersection. Faces. Faces are a very controversial item. I think the answer is you must do faces one at a time. Other people disagree. The problem is it's extremely hard to control the stimuli correctly. I'll tell you the bad example. So, one of the first claims was that you can, that an angry face will be like a red letter. It will pop out from a background of green. Angry faces should pop out in neutral faces. Well, what did the stimuli look like? The neutral faces looked like this. The angry faces look like... Yeah, that's very easy search. But the search was for white teeth. Has nothing to do with faces, nothing to do with emotion. It had to do with just a white line. And there's a lot of literature going back and forth. But the important general story is your search engine has a very limited vocabulary. It's not like Google. I can type anything I want into Google. Google will give me some answer. For your visual search engine, you can type in, I want left, but you can't type in, I want my mother, or something like that. Well, you can type it in, but you'll still have to search for her. Unless she is uniquely colored. Okay, there are two types of guidance, of this type of feature guidance. And I can illustrate those. One of them is what we call bottom-up or stimulus-driven guidance. So I won't even tell you what to look for. Tell me if you find any targets. And so I didn't tell you what the target was, right? But you, I think, decided it's these three, right? They look like targets because they are different from their neighbors. They are salient because they are different from, not because you are very excited by green verticals. Well, you might be, I don't know. But if you were, you should be excited by this one. And it does not pop out because it's surrounded by other things that are almost green vertical. So this is bottom-up, stimulus-driven guidance. If I say, did you find the target here? You say, what's the target? I have no idea. But if I say, if I now say, find green vertical lines, the stimulus doesn't change, but you can find the green vertical lines. If I now say, no, I didn't mean that, find red shallow lines, you say, okay, now I found red shallow lines. In fact, it may even look like the red ones now become a little more salient because you are adjusting the way that your top-down visual attention is being guided. Here's a cartoon of a model of the way we think this works. Front end, here's a visual stimulus. Bottom-up processes tell you where things are different from their neighbors. Top-down processes can be used to find what you are specifically looking for. So, do I have, whoop, I did. So if you're looking, okay, so here, look for red vertical lines. You can clap again if you look. Ready, find a red vertical line. Okay, very easy. How did you do this? The argument is what you did, so the bottom-up information is all just noise here, because they're all different from each other. But you said, I want red things, I want vertical things, so I'll put high weights on those. I will combine that information into some sort of a attentional priority map, and if I put my attention at the intersection of vertical and red, oh look, there's red vertical. And that's the basic idea of guided search for features. This did not work because if you say, give me red, give me vertical, you get everything here. All the objects have both red and vertical. And so that's why you have to search. So the way you configure your attentional system is you set weights on these different components. One interesting rule that probably saves you when you are crossing the street, certainly in St. Petersburg, where all the streets appear to be 8 lanes wide. But anyway, is that bottom up, the stimulus-driven attention, you cannot set that weight all the way to 0. And I can illustrate that. I want you to find green verticals in the next slide. So set your weights only for green and only for vertical, and do not be confused by anything else. Ready? Okay, thank you. So, why are they laughing? Either they think green vertical is funny, or you couldn't ignore the one highly salient object. I don't know if it's okay to call the President of the United States a highly salient object, but anyway, for today he is. Right, so your attention was automatically attracted there. You didn't get stuck there forever, right? You can then go and find the green verticals, but your attention goes to highly unique object. So even when you are crossing the street, playing with your cell phone, if you are lucky, your attention is still grabbed by the truck before it kills you. So let me show you about that. I claimed before that intersections do not guide. So look for the X's here. X or plus among T junctions. Ready? Yeah, okay, so a couple of people feel good about this. Whoops, where to go? Come on. Oh, you found that one? Did you find all of those? Yeah. Now, if those had been red, right, you would immediately see a region that was red. But here, you know, now you know where they are, but you still have to pay attention to see where that blob is. You just don't have any ability to guide attention to those sort of features. This is to prove there's really data. Right? So if I'm looking for the plus among these T's, it's very steep. It's not that you can't do any line operations. If I look for an L among pluses, that's very, very easy. Oh, by the way, the rule turns out to be that you have early visual processes that count line endings. This has 4 line endings, this has only 2. That turns out to be easy. This is gonna, I'm not gonna do this. Okay. It won't show up well enough here. So you have a basic set of features, and that's the only set you get. When you become an expert, you do not learn new features. Not in this sense. What you learn is how to use your search engine to find difficult sorts of targets. Well, like this. You see this sort of star-like structure here? That's in the medical literature called an architectural distortion. It's a sort of a stretching of the breast tissue, and it can be a sign of cancer. But when you become a radiologist, you don't suddenly develop an architectural distortion detector. What you learn is how to get your attention on that feature and then recognize it. Okay, now there's more to guiding search than just the features of the target. And one way to see that, and one way to understand what you learn, ooh, I don't know if this works here. Is there mini golf in Russia?
No.
No. Okay, this is a funny kind of golf course that you have to come to the U.S. and play mini golf sometime. It's also kind of hard to see. Golf balls. You know about golf balls?
Yes.
Yeah. Okay. Find the golf balls. Yep. Okay. Good. Maybe. You found that one. You found that one. You did not find those 5. You didn't find that one either. Why didn't you find them? It's not because... So, how do you find golf balls? The story I was telling so far says, oh, look for round, small, and usually white. And if you did that, well, that one up in the tree should have been better than the ones on... It's higher contrast than the ones you did find. But there's another kind of guidance, and we would call that scene guidance, that embodies your knowledge of how the world works. Right? So, if I am looking for, if I didn't happen to know where she was already, if I'm looking for Professor Falakman, right, where would I search? So I would say I want, things with, human features. That would be good. But I also would not waste any time. Well, there's some things with human features on the wall, right? But I know that she is not going to be hanging on the wall or on the ceiling, right? In the same way, we go forward. You know, even if you don't know about mini golf, you know that if you're looking for golf balls, they must be sitting on a surface, typically. So there are 2 types of scene guidance we can talk about. This is probably also good for, so syntax and semantics in Russian?
The same.
Oh, syntax and semantics, good. It's my kind of Russian. Okay, so the knowledge that golf balls must sit on a surface we would call syntactic guidance. It's about the structure of the world. Semantic guidance would be about the meaning. Like you know that, well, okay, where is the bottle of water? Syntax says it's not floating in the air. Semantics says it's probably not on the ground. That's perfectly legal in the physical structure of the world. But it would make more sense, more semantic sense for it to be on a surface like a table. And in the same way, golf balls here make more sense than, say, a golf ball on this surface, even though it is physically legal in both cases. That sort of guidance is a very important part of what happens as you develop an expertise. So, if we go back to eye tracking in radiology, here's a novice looking all over the place. Here's an expert. Why is the expert making fewer eye movements? It's mostly because the expert knows where cancer might be hiding in these images. And the expert, so apparently, for instance, it turns out that cancer is, for whatever reason, more common in the upper left quadrant than, say, in the lower right. And if there's not something clearly attracting your attention here, an expert says, I just don't need to look there. You have some, if I showed you this image, you would say, I have some expertise. I know if I'm looking for lung cancer, I should look in the lung, not, not over here, right? That's a stupid place to look. But as you become a true expert, you develop knowledge that will guide your attention quite precisely in many cases. You do this, you are experts for a whole range of search tasks in your regular life. So, where is the cat? You don't know exactly where in your flat the cat might be. But your search is profoundly guided, first by the features of cats. You do not look for bright blue things, unless you've done something horrible to your cat. And you look in places where the cat should be. Now, if the cat's being clever and is hidden someplace else, being an expert won't work, but usually it will work for you. Now, this is old, at least in a big medical center in the US, this is not the way you look for lung cancer anymore. What you would get is a chest CT, computed tomography image, which is really like 300 slices through the chest. Now what the radiologist is doing is searching not through a simple 2D image, but through a 3D volume of image data. How does that what does that search look like? Nobody knew. So we thought we'll find out. We'll track the eyes of radiologists while they do this task. Oh. It's okay. Actually, turn it off for a minute, because I'm going to show I want to show this, and it's going to be hard to see without light. But you can have light. People are falling asleep. So. Okay, so this is one slice through the chest. Oh, this is because I'm coming out as black. You're filming the wrong thing. The pictures are better. I'm better with the lights out. Here's the eye. This is the eye movements. But what I'll show you now is a movie as the radiologist moves back and forth through the lung, looking for what are called lung nodules. The reason we did the golf ball demo, I made this for radiologists. Lung nodules are small white spheres, much smaller than a golf ball, you hope. And they are a sign of lung cancer. Okay, is this going to run? Okay, so you can see the eyes are sitting in this quadrant, now moved up to the upper right-hand quadrant, bounces around a little bit over there, over to the left, now he's going to move up. And at the same time, the radiologist is controlling the depth with, like a mouse thumb wheel or something. So it's hard to see exactly what he was doing. Here's a way to plot this. We will color code the quadrants. And now what I'll do is I'm going to plot time on the x-axis, and I'm going to plot depth, or the slice in the lung, on the y-axis. And whoop, here's what you see. Now you can put the light if you want. At least for me. There we go. Now you can't see anything. Now you can see a little bit. You like that? That's good? Okay. Anyway, so remember, each color is a quadrant of the lung. This radiologist is sitting in one quadrant, going all the way through the depth of the lung, then picking up another quadrant, going all the way through the depth, now the green quadrant, and so on. What the radiologist is doing is staying in one position in the XY plane and drilling in Z. So we call this a driller. I don't know if is there a good Russian word for driller? Look, I got two good Russian words for drilling. Well, anyway, he's drilling. It's not we need the word, we need the jargon, because it's not the only way to do this task. Here's a different radiologist. What this radiologist is doing is moving once, quite slowly, through, this is over a minute, through the whole lung. But see how the colors keep changing? This radiologist is staying at one depth and scanning all over the image, looking for cancer. So two completely, and we ran 20 some odd, 25 maybe radiologists, and you can divide them into two groups. There are drillers and there are scanners. And these are two different populations. You don't need to go and look for the genes for scanning or something. The way you learn to be a driller or a scanner mostly is, you sat with the senior colleague who you learned from, and he said, the way we do lungs is drill. Well, he didn't say drill because nobody knew that language until we invented it, but you learn how to do radiology from your mentor. And so there are these two groups. We don't know which one is better. It's hard to tell at this point. Let me show you one more case. We'll be okay with the light. Here I'm just going to roll through one case. Again, you can imagine you're looking for, how can you tell if that's a white dot or a white tube that extends through the depth? So radiologists are looking at this. And at the end, we asked, so we did a bunch of cases. This was the last case. We said, thank you. Did you see anything unusual? No, I didn't see anything unusual. Did you see maybe, I can't know if you can see it, a gorilla? It's a little hard to see, but there's a lovely gorilla there. Oh, now you can see the gorilla maybe a little better. How many people here know the classic psychology gorilla experiment? Is this? Okay, so almost everybody. This is a classic experiment where you are an undergraduate watching a sort of a ball game. You are told, keep track of how often the white team touches the ball. In the middle of this experiment, a person in a gorilla suit walks through the middle of the game, waves, and walks out. 50% of subjects cannot report that gorilla. This is the consciousness part. When we did this with radiologists, 20 of our 24 radiologists did not see the gorilla, did not report the gorilla. Now you say, well, of course not. There are no gorillas in the lung. Why should they see a gorilla? If you are a radiologist, your task, if you are screening for lung cancer, let us say, is you look for lung cancer and you also look for so-called incidental findings. What that means is, ooh, it's fun. What that means is that maybe there's no lung cancer, but maybe this patient has pneumonia or a broken rib. You really want to see that. You really want to report that. So, if Igor, it's great, you don't have lung cancer. Unfortunately, you have a bad case of gorilla. You want to know that. You really want to know that in the US because if the radiologist misses it, a lawyer will sue you. And you'll be in big trouble. But they were looking for something small and white, and they missed something big and black and not round. This does not mean that these are bad radiologists. It does not mean they were stupid or not doing the task or anything. It means that experts, even experts working in their own domain of expertise, are using the same search engine that the rest of us are using. They've learned to use it as experts, but they don't become immune to things like, this is called inattentional blindness. You do not become immune to inattentional blindness by becoming a radiologist, for instance. You become very grumpy about it. It turns out there is social media for radiologists. After we published this, there were lots of notes about it on radiologist Facebook kind of thing. One line was, I wouldn't have missed the gorilla. They're wrong, they would have. Another, others were saying, another line was, we knew this already. Which is also true, that radiologists do understand that, that things get missed all the time. I mean, quite highly visible things. But I suspect they're the same people. We know that radiologists miss things. Me, I never miss anything. At least American radiologists, they think they have good superpowers. Okay. How can it be that you miss this sort of thing? Let's do a very simple experiment. When we did this experiment, we did it with red and green dots. But if I use a piece of modern art from the Modern Art Museum in New York City, that shows that I am a cultured person. So this is, but you know what you're looking at. This is 8 by 8 set of colored squares. It looks quite beautiful in the museum. If I ask you what color, what color is that? Red, good, or what? Yeah, it's good. So I'm going to do something extremely simple. I'm going to highlight one square. And when I highlight it, maybe I will change its color, or maybe I won't. And I just want you to say yes if I change the color, or no if I didn't. You could say da, right? I know that my 2 words of Russian I can get for this. But anyway, all right, you ready? I can't hear you. No, okay. That's mostly no's. That was a no. Let's do it again.
Yes.
Maybe no, maybe yes. Actually, it's no. All right, let's do it again.
No. Yes.
So, what you are seeing now, what you should introspect, what you should understand about what you're doing, is you have no idea. What you aren't saying, I think I really saw that change. What you are saying is, what do I think he would have done? 2 no's in a row. What is, I don't, oh, that's a no, okay. One more. Yeah, this is why you went to university, because you took multiple choice tests, right? 3 no's in a row, it must be a yes. But, look, it's a yes, beautiful. But what's really quite amazing here is I am changing fundamental colors right in front of your face, and you have no idea. Right? What you are seeing at any moment, how many of these do I have in here? Okay, what you are seeing at any moment is, so the gist, is there a Russian word for gist that makes any sense? Yeah, what's суть?
Общий облик зрительной сцены.
I like such.
That's not exactly.
That means soup or something. All right, anyway, you have the gist. You see something everywhere, and you have some idea that this is, the mix of colors and so on. You are getting one or maybe a very few objects that you are able to pay real attention to at any one moment. So, if you happened to attend to the object that I changed, it's trivial, right? I won't even go back and show you, but you know that. If you were looking at this one when I turned it red, of course you would know that. But unless you were attending to exactly that object, you don't know. And there's a theory in there about what it is you're looking at, which I will say a little more about in a moment. Now, we think this is related to the problems that you have in radiology. The radiologist, for instance, is looking through this lung. There's the whole volume of data. How do you know that you've looked at the whole lung? Well, I went through the whole thing. Maybe I'm a scanner. I went through the whole thing slowly once. I don't really know which objects I attended to. What I know is I got the gist of each slice. And as you see, you can get the gist, but still miss very salient things, like a color that changes. We can illustrate that a little more with some chickens here. Let's do it this way. There we go. Aren't they lovely? Okay, so this explains why I am, a psychology researcher, and I'm not rich for doing, video game animation. But, okay, so the theory says you have the gist of some sort of chicken statistics everywhere. You have one chicken, and you have a theory. And the theory is, I'm looking at some really stupid chickens doing a little stupid chicken dance. Right? And that works. Now, let's see. There are 20 chickens there. There are maybe 40 people here. There are 2 people in this audience who saw the chicken who fell apart. Where are you? There's 1, 2. There's a couple of other people who think maybe they did or wanted to know. Okay, anyway. The rest of you are, what? What's with the chicken? So everybody saw that image twice. Right? And it's not that you weren't looking in the right place. So if you pay attention, or look at this chicken, but pay attention over here, and you can see easily that you can see that chicken falling apart. But if you were not attending to it, you simply did not register it. It certainly got up into your eyes. We can show these things get up into your brain, but they do not reach the level of your conscious experience. What reaches the level of your conscious experience is the gist, the object, and the theory that you're looking at chicken things. Most of the time, that works fine in the real world. It doesn't work in psychology lectures because the guy is doing strange demonstrations, but in the real world, my theory is I'm looking at about 40 people. They're doing some things. Okay, I'm still looking at 40 people. I'm only actually attending to one. If Igor falls apart into Igor bits while I'm not attending to him, as long as he pulls himself back together before my attention gets back there, I just won't notice. I just will not know. And again, there are situations, particularly when you start creating artificial situations, like scrolling around through a lump, where you can have changes that occur right in front of your eyes, but you still somehow don't see them, at least not in a way that you can report. Now, gist, so I made gist sound maybe kind of bad, it's misleading. Gist is actually very useful. Whenever we talk, what time is it getting to be? Okay. Whenever we talk to experts always tell us the same thing at some point. And it doesn't matter if they're radiologists. We also work with the people who look for guns and knives at the airport checkpoint. Any search expert will tell you the same thing at some point. What they will tell you is, sometimes the image comes up on the screen and I just know it's bad, or I know it's important, or something. Right? I haven't found what I'm looking for yet, but I know it's there. You may have had this, feeling in your own life in some specialized domain. I know the cat's in here somewhere. We were wondering, so this sounds like what they're doing is getting information from the gist. We were wondering whether it's true. Oh, I don't know if blink has been translated into Russian. Anybody know? Yes? Yeah. What's blink in Russian?
Моргание.
Okay. Anyway, this is the overstated version of this. So if you read this book, you get the idea that gist is all you need. You make your decision in the first 500 milliseconds and you know who you should marry. I don't think so. But we wanted to see if this was a real effect in something like radiologists. So here's what we did. We did an experiment where we flashed a mammography image, a pair of breast images like this. Boop, boop. And we said, okay, on a scale from 0 to 100, would you call this woman back, meaning you think that there's a high likelihood that there's cancer here, or would you not? So now the first thing that radiologists did when we asked them to do this was to get angry. We would never do radiology in a quarter of a second. This is clinically irresponsible. We said, we know. It's an experiment. You shouldn't do this. It's very bad. But do us a favor. So after that, we were doing this at a national breast imaging meeting. We set up a little booth at the exhibit area, and we were running radiologists as they went by. So we got them to do the experiment. Here's how we plot the data. This is a standard ROC curve if you're a signal detection person, but we're plotting false alarms, the times when you say yes, but there was nothing there, against hits, the times you say yes and there was something there. If you are just guessing, the data lie on the main diagonal, right? If the data are down here, you did the experiment wrong. Perfect behavior is up here, right? 100% hits, no false alarms. So anything above this line is evidence. Is evidence that you're going to kill yourself. We unplug the computer. Get back in there. Where were we? Okay, data. What you can see is that even in a quarter of a second, the radiologists are doing better than chance. They can look at that image. They're not perfect by any means, but there is something in that image. Now, there would be a boring version of this experiment. Sometimes cancer is like a bright white dot. And showing that you can see a bright white dot in a quarter of a second is not interesting. But we did difficult cancers, not the very obvious ones. And we asked them, where do you think the cancer is? Once they made it rating, we said, here's an outline of the breast. Put a dot where you think the problem would. If there's a problem, where is it? They were completely at chance. They have no idea where the problem is. But they know that there is a problem there. Because that gist signal is telling them something. Oh, they were also right to be angry at us. Right? So here's the gist behavior. Here's where a real radiologist, a real expert lives. Much, much better. So you don't want your radiologist doing, breast cancer screening in 1 second. You want them to spend a couple of minutes with that image at least. But what we think is going on, the way we think about sort of the structure of our conscious experience is massive input, parallel processed input from the eyes goes through two paths. One of them goes to this very bottlenecked object recognition system where if I want to know what plus this is or whose face that is, I must attend to that object. That's this bottleneck right here. But there's this other pathway that fills in the rest of visual experience. We can call that a non-selective pathway. You don't want to give it too much power. You don't want to say more about it than say that it can do more than it can do. You can't read the newspaper with this. But the raw statistics of the image will tell you something about what's going on. And if you and I do the mammography task in a quarter of a second, we're right on that chance line. We have no idea. That's the expertise lets you know, oh, these image statistics mean trouble. You have the same sort of thing. Well, if you get out of a subway stop where you have never, in some part of town where you have never been before, you get up above ground, you look around, you have an instant idea about whether or not this is a safe neighborhood, right? That makes sense? You might not be perfectly correct, but you won't be a chance because you are a neighborhood expert. Something about the statistics, even in a very brief flash, will tell you something. and the experts can use that in their own domains of expertise. So, let's see. Can't see, I think. Okay, I have time to tell you one more story. I mentioned at the beginning, when is it time to stop searching? Think about the problem for the radiologist. Will stick with this breast cancer example. If in North America, if you read 1,000 cases, there are probably about 3 cancers in there on average. So a third of a percent. Very rare. You want to find them all. Most of the time there is nothing there. And you need to get home to dinner. When should you stop searching if you haven't found anything? That's a difficult problem. And it's the same thing with, with many tasks that you put down the key somewhere. You think, it must be in this room. When do you stop searching? Or at least, when do you move to the next room? That's a difficult problem. We're interested in this, particularly in this case of low prevalence searches by experts. There are lots of these. So this, for example, is what a test for cervical cancer looks like. Lots and lots of cells. You're looking for a few bad cells. Another very difficult visual search task. Or here's a different task. You do not want to get on the plane where the prevalence of threat objects is 50%, right? That's not good. Right? If you think about doing experiments in the lab, if you were doing a visual search experiment in the lab, there's targets on half the trials, maybe nothing on the other half. But that's really not true in something like the airport. Can you find the threat here, by the way? Anybody know what there is if you were a good airport screener, you would not let this bag onto the plane.
Something looking like scissors.
Yeah, so people think that these are scissors. They're not scissors, they are eyelash curlers. You can take your eyelash curler on the plane, it's okay. But that's a knife. And you don't want to let that on the plane. And that's a really easy example. Right? Knives and guns are relatively easy, particularly if they're just sitting in the image plane. Not so easy if they're on edge. What's really difficult is bombs. That's what you go to airport screener school. Wait, I will give you a quick lesson on how to find bombs and X-rays. But just in case the psychology career doesn't work. The colors are the density, that it's a dual energy X-ray, it's giving you information about the density of the material. Blue is metal, orange is organic material. What you are looking for when you are looking for a bomb is a piece of something organic that's big enough to blow a hole in a plane, and a detonator, something that will blow up that stuff if it is indeed explosive. And it can be any shape. It's the problem with plastic explosive. It can be any shape, and many things mimic the density of plastic explosive. So glossy paper magazines look beautifully like sheet explosive. Honey looks like, is very much like a plastic explosive. Lots of things. So if you want to try this, you shouldn't try this. But if you want to try this and you didn't really want to fly, you go and buy a sausage and take the earphones from your iPod or something. Wrap it around the sausage. stick the little metal piece in the sausage, and then you can. And then when they pull you aside, you can say, "I was just doing an experiment." Good luck with that. So anyway, when we do this in the lab, we only use guns and knives because explosives is just too hard. It's really a very, very hard task. But so we did this experiment with luggage stimuli. So we can imagine it like this: take 20 suitcases with guns and knives in them, and we can either put them in a stack of 40. So that would be 50% prevalence. Or we can put them in a stack of 1,000. So that's down to 2% prevalence. Does that matter? And, this is my official US government. I promised the government I would say this. These are not real airport screener data that I am showing you. Because if this was airport screener data, I would not be allowed, this is error rate. I would not be allowed to show you the real error rates. I've done this with real airport screeners. I know the real error rates. I can't tell you. I couldn't even tell you if you were in the US. I can't tell American audiences either, so don't feel bad about it. I can tell you the error rate is not 0, in case you were wondering, for real airport screeners. But you knew that. So our volunteer subjects on this task at high prevalence, so when the threats are there 50% of the time, they miss 20% of the threats. The actual number doesn't really much matter, that's just, you can scale that anywhere by making the task easier or harder, but when you make the targets rare, now they miss twice as many. Same threats, the only difference is that they are rare. If you look at the false alarms when they said there is a threat and it was not present, it goes the other direction. If you're a signal detection person, you know this as a criterion shift. Is that jargon we should translate?
It's almost the same. Спин критериев теории обнаружения сигналов.
Okay, it's got more syllables, but I heard criterion in there somewhere. Anyway, basically, when things become rare, you are much less willing to say that they are present, which is sensible, but it's not good in these tasks where finding rare targets is the job. You know, if I say, "Oh, look, I think I just saw a whale out there in the river," you know, you should require a lot of evidence for that. That would be, I think, a very rare event. But if I'm trying to find cancer or I'm trying to find bombs, you want people to find those rare things. Now, quickly, we did the same experiment with radiologists. You can't ask radiologists to come to the lab and read 1,000 cases. They only might read 5,000 a year. So what we did, this is my chief of radiology, breast imaging, and one of my postdocs, we took 100 cases, 50 with cancer, 50 without, and we slid them into regular practice at the hospital. Less than 1 case a day. So our radiologists are looking for these things as though it were their real task, as though they are saving lives and all that good stuff. And then, so that's the low prevalence case. And for high prevalence, we just got them to read 100 cases for us. And the data look the same as what I just showed you. More than twice as many errors at low prevalence. Somewhat fewer false alarms, but it's the miss errors that are really important. So if we go back to the beginning, what this is telling us is that maybe half of the miss errors in breast cancer screening can be explained by saying we just aren't good at looking for very rare targets. It doesn't matter if you're a wonderful radiologist. You're still being a radiologist, you're still being a human radiologist, and that means that rare things are going to be hard to find. You get the same pattern of results with airport screeners. I can't tell you the real numbers. But you get the same pattern. There's no reason to think that anybody is particularly immune to this. The real trick would be to figure out how to cure it. What can you do that would cut down those errors? But I've run out of time, and I also don't know the answer to this. No, I haven't really run out of time, but I really don't know the answer. I give talks about this in the hopes that somebody will ask a clever question that I can go and use as part of the answer. So I will stop. Thank you very much, and I will answer questions if people have questions. So, Russian, yeah, now you can turn on the lights.
Вопросы можно задавать по-русски, если кто-то не хочет по-английски.
And you can ask Russian questions that I can translate. I want to hear the Russian version. No.
Your gist data, where you vary the length of the exposure.
Yeah.
The gist, the information from the gist improve between, let's say, 250 and 1,000.
So, yeah, you get somewhat better. I think it wasn't actually statistically significant, but you do get better with more time. But that's unsurprising, in part because every second you can get, 20, 40 deployments of attention, and you might get lucky and find whatever it was. It would be tricky to try to figure out how to just have long gist without any focal. Well, you do know that.
You don't think the improvement is from an improvement of the gist?
Well, there may well be an improvement in the gist information too. It's probably just yet one more diffusion process running to completion. But so actually the only reason that we ran, what he was noticing is that we ran several flash durations in that flash, the X-ray experiment. The reason we put the longer ones in there was because it made the radiologists less grumpy. We really only wanted the short. So when you're doing these sort of experiments, you typically don't want people moving their eyes. If you flash for a quarter of a second, you probably don't have a deliberate eye movement. And anything longer, and they're starting to make strategic eye movements. But we had to put them in there because otherwise the radiologists wouldn't play, and they got all angry. So it's important to keep the subjects happy. Yeah.
Thank you, Michael. My question is about how can we improve the productivity of the radiologists, taking into account all these findings? Not just describe, but improve.
Well, okay, so that of course is I keep telling U.S. granting agencies that I know the answer to that. And I keep being wrong. But they keep sending money anyway, so it's okay. There are some things we know would help, but it's interesting that they do not help as much as you might think. So, for example, if you were missing 20% of cancers, hey, let's get 2 radiologists to look at the image, right? And probability, first year probability says 0.2 times 0.2, the error rate is now only 4%, right? That's wonderful if the errors are not correlated, but the errors are strongly correlated. And so many countries, does anybody know anything about radiology in Russia? No? Oh, yeah, okay. Do you know if Russia double reads mammograms or not? So there are some countries in Europe where every case is read by 2 radiologists, not in the US, mostly for financial reasons. It's just more expensive. You get a benefit from 2 readers, but it's a small benefit. All right, let's not use 2 radiologists. Let's use 1 radiologist and 1 computer, because the world is full of clever computer scientists who say, okay, I'm looking for, let's do lung cancer. I'm looking for white round objects. How hard can it be? And the answer is, I can build These are called computer-aided detection systems, or CAD, C-A-D. I can build CAD systems that are really very good. They're about as good as a good radiologist. So now we'll put a good radiologist together with a good computer, and it should be significantly better. It's a little better. And the improvement is so small that there's a major argument in the US literature about whether you should use CAD, or more precisely, whether you should pay for it. CAD is used very widely in US medical practices because if you push the CAD button, I think you get an extra $5 for each case that you do. Why doesn't it work? Well, let's go back to this problem of if the computer was perfect, you just send the radiologist home, right? That's fine. But the computer isn't perfect. It's about as good as the radiologist. A good radiologist and a good computer will find, let's say, 90% of the cancers and will false alarm 10% of time. That's pretty good. Now, think about that in clinical practice. I have 1,000 cases. There are 3 cancers in there. Let us assume that the CAD system finds all 3 of them. It also finds 10% of 1,000, 100 false alarms. So it is putting a mark on the screen. You know, it's saying, hey, radiologist, look here. 3% of the time, it's right. If your friend is giving you advice, you know, you really want to go out with that person. You know, he's wonderful, she's wonderful. And they're right 3% of the time? Do you listen anymore? We don't know that this is true, but we think that the reason CAD systems do not work terribly well is because radiologists are systematically ignoring the advice because it's mostly pretty bad advice in an objective kind of a way. So there are lots of things that should work. We haven't found the magic. Did I answer anything like your question? You asked a question half an hour ago. But the short answer is there's lots of room for more clever ideas.
Thanks. You've mentioned during the lecture that we do not learn new basic features. But as far I remember Anne Friesman's lectures and her paper of 2006, she claims that we can learn more complex features during our lives, maybe animal features such as legs and vehicle features.
I know that.
So what do you think about it?
Much as it pains me to ever contradict Anne, who's my closest and senior scientific colleague, I think she's wrong about that. Now, part of, but this is debatable, right? And there are actually, she has usually, if I'm making this argument at more length, she has some of the best data against the idea that you can make new features. She trained subjects, she and Dj, if you've seen that paper, she trained subjects for like forever on one particular task. They got better and better and better. If you had a new feature module, it should transfer to other related tasks, right? So if red attracts attention in a visual search task, red should also attract attention when it's the color of the sign on the street, that kind of thing. What Treisman and Dj found was almost no meaningful transfer to anything else. What's difficult, so everything improves with a lot of practice, and what's very difficult is to tell the difference between having a new feature and having a better way of using old features. You can really see this in the old attention literature. It's the definition of old. If you think the old attention literature is my stuff, forget it. So even older. back in the 60s and 70s, most of the work is done with letter stimuli. And people like Schifrin and Schneider, brilliant papers, among other things, argued that you learn how to find, a particular letter by, in effect, growing a new detector for that letter. But it's extremely difficult to correctly balance all the low-level visual features, that define the difference between the letter K and the letter R, or something like that. And the reason that there's still fights about it is because it's very, very hard to do exactly the right experiment. So, if you believe me, the answer is you can't grow a new one. If you believe old Anne Treisman, she would agree. 2010, she changed her mind a little bit, but she's retired now, so it's back to it's still worth doing research on that. Time to do something else? What do you think? One more question.
The question is, it's clear why we need the gist. It's clear why we need the focused object processing. But the question is, why we need the split these two systems? What's the biological, the evolutionary meaning of their divergence?
So the problem is you simply can't do the focused attention. The focused attention system has to be ferociously, very powerfully limited, because otherwise you run out of brain very quickly. So John Sotzos did a lovely calculation once upon a time. He built a little toy system and said, okay, let's imagine that we will process, instead of just processing one object, we'll process all the objects, for this recognition binding part. And nothing fancy like faces, he's just doing colored lines in different orientations. And he's doing a little back of the envelope calculation, and the brain that he required for this turned out to be larger than the size of the known universe. And he decided that this was not practical. So I think the answer is that the computational requirements, and actually Sotzos has a lovely book on this, if you want to, the long version of it. The computational requirements of object recognition are so profound that they have to be restricted, say, to one object, or maybe a very small number of objects at once. But if that was everything, then the rest of the world would sort of be, I'd attend to you and everything else would go away. That's not good either. So we seem to have evolved this very powerful binding recognition system, and also what you could think of as a quick and dirty do-it-everywhere system. And they are separate, I think, for sort of neural computational reasons. You just can't do both of them everywhere all of the time. Is that more? Did you want to translate that? Good luck. Does that make sense?
У них могло появляться ощущение, что цель там есть, однако они не могли понять ее положение конкретно. Однако у них было представление о том, что они есть, то есть с разных карт они смогли соединить представление в единый какой-то образ.
So when we look at the airport scripts, they've got the gist of the situation, and they've got the idea that the target is present. Is this idea of the present target coming from the gist, or is it coming from the object recognition system? And if it does come from the object recognition system, why the person cannot join the two sources together?
Yeah, no, I think that the feeling that there might be a threat here is a gist signal. And
только из общего адреса сцены идет удовлетворение, потому что там должно быть есть целевой стимул. Вторая система просто не срабатывает.
And the interesting part of that is you don't know which object it is that's worried.
Что это за неправильный объект, просто что-то запрещенное. Что именно?
But it's, when you're doing the real airport screener task, it's complicated because you don't get a quick flash. It'll be up there while you are doing gist in this part of your brain. You are also going object, object, object. And then you're saying, what is that? And you're thinking hard about that object. And now you're trying to trace this little piece of wire or something and see if it goes someplace. If you're looking for orange things and a wire, just think about what you packed the last time you flew somewhere. Oh yeah, I need 15 adapter plugs for all of my equipment, and the computer has to come out because it's just got so much electronics in it, it hides everything else. So now you have to start doing, we could talk about object tracing, that's a different... Anyway, you're using both of these pieces of your system all the time when you're doing normal vision and certainly when you're doing airport screening. They may be physiologically separate. I don't really want to, I don't want to say that too seriously, but if you think about the what and where distinction in sort of standard models of the visual system, if you lesion in the parietal lobe, you get real problems with, sort of gist-ish, gist-like functions. If you lesion in the temporal pathway, you may be able to see where all the objects are just fine, but you don't know what they are. So it's possible that this non-selective, selective distinction really reflects visual system structure too. But I wouldn't swear. If Igor says it's not true, I would argue with him. Okay? Thank you. One more. Thank you anyway.
There is maybe myth about specialists or people who have a large expertise in some field. So you have a great expertise in people who have expertise. So I just wanted to know, is it true that they cannot verbalize their knowledge? So they cannot verbalize the rules how they search the cancer, for example?
So the answer is yes and no. So it is. You can certainly. So if we take the example of radiologists, they are certainly passing on important parts of their expertise by saying, we are looking for round white things. This is a round white thing. Look for that. But it is generally true that we have very poor ability to verbalize the perceptual processes sort of at a layer behind that. You don't know where your eyes have been, for example. So if you say the way we do this, you wouldn't particularly, you might say I drill or something like that. But if you ask a radiologist or any of us, where did you just look? It turns out that I do not know any more about where I just looked. If I put up a scene, put up a picture, and I take it away and I say, okay, so it's 3 seconds, there are 12 fixations, put a dot for each fixation. I can do that, it won't be random. If you ask me, okay, where did I just look? Okay, there, something. I didn't look there, I know that. But if I get Igor up here, and you ask me, where did Igor look? My answer is the same. I know where a sensible person would look, but I don't know where I particularly look. If you asked somebody who didn't take a sensation and perception class, maybe even if they did take a sensation and perception class, explain to me exactly how you know that you are further away than you are. They'd come up with something, but they would miss many, many of the cues that we use. You just don't have introspective access to a lot of that. And what you are describing is actually, I think, chapter 1 of the Gladwell book. He talks about, I think, a sculpture expert who takes a look at a sculpture and says it's a fake. And they say, well, why? Unpack that. I got no idea, but it's a fake. And in this particular example, it's true. Apparently, it was a fake. So that it's true that you can often have very little ability to describe exactly. Well, think about driving. Ask yourself, or think about, well, better yet, think about talking. If you ask me, I can talk. I've been doing it for hours here. You're saying, I gotta go. Where have I put my tongue? And where, if I want to say, please write down, where do you move your tongue if you want to say Falikman? Okay, I'd say, you have no idea. You just do it because you're an expert on this. And so those sorts of expertise you just are not good at describing. If I become an expert speech pathologist and you're not saying Falikman correctly, which I'm probably not, you can teach me a few things, but you don't know how you're walking, you don't know how to ride a bicycle, all these sort of expertise, you don't have introspective access to all of that. And expert radiologists, they have marvelous theories. So, one more thing. One of the real problems with working with radiologists is that they are extremely smart, extremely competitive, extremely good at what they do, but they are not raised as experimental scientists. And they think, mostly, that what we are there to do is to confirm that they were right all the time about their introspection. And they have all sorts of theories about how they find cancer or whatever. And some of it is transparently nonsense, which you don't say to them because that's rude. But it clearly cannot be how they're actually doing the task. But it's very hard to get them to believe that. But so the answer is yes and no. Sorry.